Welcome students. It's quite unfortunate that again we are meeting in online classes. So we don't have other alternatives now. So without wasting much time, we'll start with the next topic. So what is the topic you will come to know in between my discussion. You just concentrate on the examples which I am quoting now. You think about particle having a mass m moving along the circumference of a circular path with the uniform angular velocity. I said consider a particle having a mass m continuously moving along the circumference of a circular path with the uniform angular velocity. Of course, you called this as uniform circular motion in once upon a time. You think about one more example, second example, satellites revolving around the planets in a circular orbit. Think about the third example which I am quoting now, planets revolving around the sun in an elliptical path. Think about the one more example, fourth example. Think about this experiment which you have performed in your physics lab. Finding the effective length of a pendulum, a simple pendulum experiment. You know, in that experiment, there was a metal bob hanged from a rigid support using a string having a certain length. During the experiment, you have given an oscillation to this pendulum. In order to give the oscillation to this pendulum, you are asked to take this metal bob slightly away from its original position. You may be knowing technically this position of the bob where it was at rest initially is called mean position. I am going to represent as m. I said in order to give an oscillation, you have taken the metal bob to one side, slightly away from the original position. You can call this position as an extreme position. You have called this position as an extreme position. Of course, you might have come across this example in tackling one of the problem in a topic called work energy power, right? After taking the bob to an extreme position, you will leave the bob from extreme position. When you leave the bob from extreme position, what you have noticed is this bob will start moving towards the mean position, and while it is moving towards the mean position, you know its velocity goes on, increases. By the time it crosses the mean position, by the time it reaches the mean position, its velocity is maximum, and since its velocity is maximum, due to inertia of motion, the bob will start moving towards the other extreme position, and while it is moving towards the other extreme position, you have noticed that its velocity goes on, decreases, and again it will stop at the other extreme position. Again it will start moving back towards the mean position, and after crossing the mean position, again it will start moving towards the extreme position. What I mean to say that you have observed that once you leave the metal bob from an extreme position, the metal bob, or in other word I can say simple pendulum, will exhibit an oscillation. This metal bob exhibit an oscillation about the mean position, correct? This is the fourth example. Fifth example, you might have come across this also in your physics practicals. There was a rigid support, and there was a spring hanged vertically from a rigid support, and to the other free end of the spring you have added some load, means you are adding some mass, and when you say you are adding some mass, there will be a weight, and that weight is m into g, is acting vertically downward. I can call it as a load. There is some load added to the free end of the spring, means I am talking about the experiment called spring constant experiment. There you have come across the spring, and you are adding a load, and when you are adding the load, the reading of the pointer on the scale keeps on changing, correct? Yeah. Now, I am not talking about that experiment, but instrument is the same. There is a spring hanged from a rigid support added with some load. Now, what I will do is, I will stretch a spring through a small distance by pulling it slightly downward. I will stretch a spring by applying a small amount of force by pulling it through a small distance downward. Let us say I have pulled the spring through a distance x slightly downward. Now you will find that the new position of the load is somewhere here. Since you have pulled it, the new position of the load is somewhere here. You have pulled it through a distance x. After pulling through a distance x, now I am going to leave it. If you try this, when I leave it after pulling through a distance x, you will find that this spring will execute an oscillation about this original position. Original position, technically I can call it as a mean position, and after pulling through a small distance, this has occupied the new position. I can call that position as an extreme position. When I leave that load or a spring from the extreme position, you will find that the spring will try to go back to its original position, which is called mean position. By the time it reaches a mean position, it will gain some speed due to inertia of motion. Again, it will go slightly above its mean position, and after reaching a certain height above the mean position, you can call that position as an extreme position. Again, it will try to come back to its mean position downwards. Means what you observe here is, here you find a oscillation of a spring, or I can also call it as a vibration of a spring. Spring will be vibrating about the mean position, or spring will be oscillating about the mean position. This is the fifth example. Even you can think of one more example of a tuning fork. You might have heard about it. Tuning fork is an instrument using which you can produce a sound of particular frequency. Some of you might have seen that instrument. See the external features, how it looks. It is made up of a metal. The structure looks like this. And on the tuning fork, there is some value will be printed. Let us say here the value printed is around 384 hertz. 384 hertz. Now, what is the meaning of that value? If you excite a tuning fork, question arises how to excite a tuning fork. You have to hold a tuning fork here. These two are called prongs of a tuning fork. Prongs of a tuning fork. You hold a tuning fork here. Strike one of the prong of a tuning fork on a rubber pad. By striking one of the prong of a tuning fork on a rubber pad, you can set the tuning fork into vibration. Or you take a wooden hammer, one more method, wooden hammer. Using a wooden hammer, strike over one of the prong of a tuning fork. That time the tuning fork will set into vibration. When this tuning fork is set into vibration, it will vibrate like this. The prongs of a tuning fork will vibrate like this. This is the original position of the prongs. We can call it as a mean position. When they vibrate, the prongs will move slightly inward. Again, they will try to go back to their initial original position, so called mean position. Again, they will move slightly outward. They vibrate like this. When they are vibrating, they vibrate with this frequency. If the tuning fork is proper and the value printed is proper, they will vibrate with that frequency, and when they vibrate with that frequency, they will produce a sound of that particular frequency which is printed over it. So, this tuning fork will be vibrating about its original position. You can call these positions as extreme position for your reference. Vibration of a tuning fork. So, actually for your information, there is no much difference between the word oscillation and vibration. Soon we are going to come to know the difference between the word oscillation and vibration. What is the difference? You will come to know. Vibration is also an oscillation only. Look at these 6 examples which I quoted. First example was particle of mass m continuously moving along the circumference of a circular path with the uniform angular velocity. In a simple word, particle exhibiting uniform circular motion. Then I said satellites revolving around the planet in a circular orbits. Then third example which I quoted was planets revolving around the sun in elliptical path continuously. Fourth example I quoted was oscillation of this pendulum, simple pendulum. Fifth example which I quoted was oscillation of this loaded spring or vibration of this loaded spring. Sixth example which I quoted was vibration of a tuning fork, prongs of a tuning fork when it was excited. Even I can add one more example. That time I mentioned one example, planets are revolving around the sun in an elliptical path. Similarly, these planets, for example, if I take our own planet Earth, they exhibit a rotational motion about its own axis, revolution and rotation. Planets are revolving around the sun, along with the revolution they also exhibit a rotational motion about its own axis. In all these examples, I was concentrating on the one particular type of a motion exhibited by the objects during uniform circular motion, during the motion of a satellite around a planet in a circular orbit, during the motion of the planet around the sun in elliptical path, or revolution of the planets around the sun elliptical path, or rotation of the planets about its own axis, oscillation of a pendulum, oscillation of a loaded spring, vibration of a excited tuning fork, all can be considered as a periodic motion. All can be a periodic motion. What do you mean by periodic motion? In a simple word, a motion which repeats itself at a regular intervals of a time is called periodic motion. A motion which repeats itself at a regular intervals of a time, we can call it as a periodic motion. Oscillation of pendulum can be a periodic motion. Oscillation of a loaded spring can be a periodic motion. Vibration of a excited tuning fork can be a periodic motion. Even uniform circular motion is also a periodic motion. And the motion of the planet around the sun in elliptical path is a periodic motion. If you take an example of Earth, Earth will complete one revolution, means it will take around 365 days to complete one revolution, and the same motion is repeated itself at every 365 days. Earth will take 24 hours to complete one rotation about its own axis, the same motion is repeated for every 24 hours. All these examples which I quoted can be called as a periodic motion, means in a simple word I said a motion which repeats itself at a regular intervals of time is called as periodic motion. With reference to this periodic motion, I can introduce some technical terms. Obviously, it is not new to you. We already come across these words in the earlier discussion. There is something called time period of periodic motion, which we represent by the symbol capital T, followed by frequency of a periodic motion, which we represent by the symbol F. I said no, these two things are not at all new to you, because you already introduced these two terms in a circular motion. We defined a time period of circular motion, we defined a frequency of a circular motion, correct? What do you mean by time period of a periodic motion? Very simple. The time taken to complete one revolution, or time taken to complete one rotation, or time taken to complete one oscillation, time taken to complete one oscillation, or time taken to complete one vibration. If I proceed further with many other examples, we can come across something called cycles. Time taken to complete one cycle can be a time period of a periodic motion. Of course, you use one word, that is enough. You need not go for a number of times repeating the same thing. Time period of periodic motion is a time taken to complete one revolution, or time taken to complete one rotation, or time taken to complete one oscillation. Any one word, if it is enough. Time taken to complete one vibration, or time taken to complete one cycle. That is called as a time period of a periodic motion. What do you mean by frequency of periodic motion? Number of cycles completed in 1 second, number of revolutions completed in 1 second, number of rotations completed in 1 second, or number of oscillation completed in 1 second is called frequency of a periodic motion. And you must be knowing that the frequency is nothing but reciprocal of a time period. And you know the reason behind that also, why frequency is equal to reciprocal of a time period. Very simple logic is, you consider this proportion, number of oscillations and the time taken. If you talk about one oscillation or one cycle, one revolution or one rotation, what is the time taken is called as time period T. To complete one oscillation, the time taken is called time period. That is the definition of time period. The time taken to complete one oscillation or one cycle or one revolution or one rotation is the time period T. I would like to know frequency of oscillation means number of oscillations completed in 1 second. This is called frequency of oscillation. Cross multiply, you will get this relation. F into capital T is equal to 1 or F is equal to 1 by T. This is the relation. And you know, time period SI unit is second, frequency SI unit is per second, is nothing but hertz. Per second is nothing but hertz. 1 per second is taken as hertz. Remember this. Now coming to the topic which I actually supposed to discuss. Of course, I started with the word periodic motion. I have introduced a term called time period of periodic motion. I introduced a term called frequency of periodic motion. But ultimately, the topic of discussion according to our syllabus is this topic called oscillation. That is our main topic of discussion. Of course, this word we already used in my explanation. What do you mean by oscillation? Very simple. If you refer the examples which I quoted, around 6 to 7 examples I have quoted, but in all the 6 to 7 examples, all the 7 examples are not oscillation. I said the topic of discussion is oscillation or oscillatory motion. To call any motion as an oscillation or oscillatory motion, I can define something like this. If a particle is said to have to and fro motion about the mean position or up and down motion about the mean position, we call it as an oscillation. Oscillation or oscillatory motion is defined as, or a particle is said to have an oscillation or a particle is said to have an oscillatory motion if the particle is having a to and fro motion about the mean position. Look at this oscillation of a pendulum. It is an example for oscillatory motion. Look at the oscillation or vibration of this loaded spring. It is an example for an oscillatory motion. Here, pendulum is exhibiting a to and fro motion about the mean position, correct? And here, loaded spring is exhibiting a up and down motion about the mean position. Here, the prongs of a tuning fork is having a to and fro motion about the mean position. They are all example for oscillatory motion. A body is said to have an oscillatory motion if it exhibits a to and fro motion about its mean position or up and down motion about its mean position. If that is oscillatory motion, now think about the first example which I quoted. Uniform circular motion. Particle is moving along the circumference circular path with a uniform angular velocity. Is it oscillatory motion? Not at all. There is nothing like a mean position there. If you take one more example which I quoted, satellites are revolving around a planet in elliptical path. Is it oscillatory motion? Not at all. There is nothing like a mean position. If you take one more example, satellites are revolving around the planets in a circular path. It is not oscillatory motion. Planets are revolving around the sun in an elliptical path. I will repeat again the last two examples. Satellites are revolving around a planet in a circular path. Planets are revolving around the sun in an elliptical path. They are not oscillatory motion, but they are periodic. Even rotation of Earth about its own axis, it is a periodic motion, but it is not oscillatory motion. Means what I am trying to conclude here is, all the oscillatory motions are periodic. All the oscillatory motions are periodic, but all the periodic motions need not be oscillatory. We know oscillation of pendulum is a periodic motion, it is oscillatory motion also. Oscillation of a loaded spring or vibration of a loaded spring is a oscillatory motion and also periodic. vibration of excited tuning fork is obviously oscillatory as well as periodic, but uniform circular motion of a particle is not a oscillatory motion, but it is a periodic motion. Motion of the satellite around the planet is a periodic, but it is not oscillatory. Motion of the planet around the sun is a periodic, but it is not oscillatory. Rotation of the earth about its own axis is a periodic motion, but it is not a oscillatory motion. So, at the end what I want to conclude here is all the oscillatory motions are periodic, can be periodic, but all the periodic motions need not be oscillatory. I think ideas are clear to you. Let us proceed further in this topic. The topic was named as oscillation, but here more things we will discuss related to the oscillation. Let me introduce something called simple harmonic motion. This concept is very much important for the 2 years of physics. In a short form, we call it as simple harmonic motion as SHM. See this example which I am having on the board, oscillation of a simple pendulum is actually one of the example for a simple harmonic motion. Oscillation of this loaded spring or vibration of a loaded spring is also one of the example for a simple harmonic motion. Now see again confusions may arise in your mind. I started with a periodic motion, then I introduced in between oscillatory motion. Now I am talking about something called simple harmonic motion. I said out of the given examples which I mentioned, I can say that oscillation of a pendulum is an example for a simple harmonic motion. See, remember, point to be noted is I did not explain what do you mean by simple harmonic motion. Before that only I am mentioning an example. There is a reason. Oscillation of a pendulum about its mean position is all example for a simple harmonic motion. Oscillation of a loaded spring is also an example for a simple harmonic motion. Now the next question is, under what condition you can call a motion as a simple harmonic motion, in a short form SHM. A particle or a body is said to have a simple harmonic motion if the first required condition is acceleration of a particle is always directed towards the mean position. This is the first required condition. A particle is said to have a simple harmonic motion if the acceleration of a particle is always directed towards the mean position. And the second required condition is magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. Let us try to understand these two conditions. What do you mean by that? This is a very important conditions. You must be knowing the meaning of it, not simply remembering the conditions. You should know the meaning of it. What do you mean by that? I said the particle is said to have a simple harmonic motion. The first required condition is the acceleration of the particle during the motion is always directed towards the mean position. And the second required condition is magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. Let us try to follow. What do you mean by that? By taking the examples which is already there on the board. Let me start with an example of a simple pendulum in understanding these conditions. Because you already performed an experiment with the simple pendulum, you will be having a better idea. With that intention, I will be taking an example of a simple pendulum in understanding those two conditions. I already told you oscillation of a pendulum, even oscillation or vibration of a loaded spring is an example for a simple harmonic motion. Of course, that time I told you there is no much difference between oscillation and vibration. If the frequency of oscillation is more, then we call it as a vibration. If the frequency of a oscillation is more, then we call that is as a vibration, that is all. Vibration is also oscillatory motion only. See, when the frequency of oscillation is high, you know what do you mean by frequency? Number of oscillations completed in 1 second. If it is very high, then we can call that that particular oscillation as a vibration, that is all. Okay, coming to this. As you already know that in the example of a pendulum, I will redraw it just to convince few points. There is a rigid support and a metal bob was hanged from a rigid support. This position of the metal bob, initially where it is at rest, is called mean position, you know it. In order to give an oscillation, you will take a bob to one extreme position, means you will take a bob slightly away from the original position. You can call it as an extreme position. When you have taken a bob slightly away from the mean position to one side, can you see the new position of the thread make some angle theta with the vertical or with the original position? Surely this thread has got some length. Actually, the effective length of the pendulum is from the rigid support to till the center of mass of the bob. From the center of mass of the bob, actually this metal bob is spherical in shape, and since it is a standard shape, assuming that mass is uniformly distributed, entire mass of the bob is assumed to be concentrated at its center. It is called center of mass. Effective length is measured from the center of mass to till the rigid support. Let us say length is L. Fine. As you already learnt in a topic called work energy power, or maybe in a laws of motion, when the bob was held in that extreme position, when the bob was held in that extreme position, I said held, don't you think it is in equilibrium? When the bob was held at that extreme position, the bob is at equilibrium. Of course, it is called static equilibrium. You know the meaning of those words. Equilibrium means number of forces are acting on a body, but the net force is 0. That is called equilibrium. And there can be a static equilibrium, there can be a dynamic equilibrium. Static equilibrium is the one where the number of forces are acting on a body, net force is 0, body is at rest. Dynamic equilibrium is the one where number of forces are acting on a body, net force is 0, but body is moving with the uniform velocity. But here it is a static equilibrium. The bob is held at this extreme position, means it is at rest. How many individual forces are acting on a bob? 3. One is a tension, one more is a weight mg, and one more is a force with which you have pulled a bob to an extreme position, correct? This is the mean position. At equilibrium, when the bob is held at that extreme position, the net force acting on a bob is 0. Net force is 0, even though there are 3 individual forces are acting on a bob: tension, its weight mg, and there is a horizontal force, horizontal force with which the bob has been pulled to a side. So net force is 0. And you have balanced it also, like you have resolved T, correct? T cos theta balancing mg, T sin theta is balancing F, net force is 0. At the time when you leave the bob from the extreme position, what do you mean by you are leaving the bob from extreme position? You will be removing this horizontal force what you applied. You will leave the bob from your hand. As long as the bob is held at the extreme position in your hand, you are applying some horizontal force with which the bob is held at that position, and 3 forces are acting, net force was 0, correct? Isn't it? You know how it was balanced also. I said you resolved T, one component here, T cos theta, when it was at equilibrium, this is theta, correct? No? This is T cos theta, this is T sin theta. T sin theta was balancing F, T cos theta was balancing mg. That is what you have learnt. Correct. Now when you remove this F, don't you think that the bob is not in equilibrium? In the presence of that F which you applied, the bob was in equilibrium. When you remove that F, there are two forces are acting, one is the tension and other one is mg. Now bob is not in equilibrium. Since bob is not in equilibrium, indicating that there is some force acting on the bob, correct? What you find practically was bob will start moving towards the mean position. Exactly. The bob starts moving towards the mean, that is what you find. The bob starts moving towards the mean position means there must be some force acting along that direction. No. Since it is not in equilibrium, once you remove that F, which is the horizontal force you applied, or once you leave the bob, you will find that the bob will start moving towards the mean position in this path. Bob will start moving towards the mean position in that path. Whether the path in which the bob is moving, is it a straight line path? Not at all. It is a part of a circle. In a simple word, it is an arc. Once you leave the bob from extreme position, the bob will start moving towards the mean position. The path in which the bob is moving is not a straight line, it is an arc. It is a part of a circle, it is an arc. Length is an arc length. In that path, the bob is moving. Obviously, it indicates that bob is not in equilibrium. There is a force acting on the bob, and moreover, what you have learned was, at the time when the bob was held at the extreme position, its velocity was 0. When the bob was left from the extreme position, the bob will start moving towards the mean position. When the bob is moving from extreme position to mean position, its velocity goes on, increases. That is what you have learnt already. That is what you already know. When the bob starts moving towards the mean position, velocity of the bob goes on, increases. Question arises. Why velocity is increasing? Because there is an acceleration. Because there is an acceleration. Since there is an acceleration, because of which the velocity goes on increasing. Next question is, who is that acceleration? Who is providing that acceleration? Wait for some time, you will come to know. But one thing is clear, when you leave the bob from extreme position, at the extreme position when the bob was held, its velocity was 0, and by the time the bob is coming towards the mean position, its velocity goes on, increases, gives a clear indication that there is an acceleration. And already you know that velocity of the bob is maximum when it reaches the mean position, and by the time it reaches mean position, due to inertia of motion, again it will continue to move towards the other extreme position. While it is moving towards the other extreme position, its velocity goes on, decreases, indicating that there must be a retardation or negative acceleration. When the bob is moving from mean position to extreme position, its velocity is decreasing, means there must be an acceleration in a direction opposite to direction of motion. Correct? So, I will give you one simple idea to understand this. You drop an object from a certain height above the ground. Of course, whatever I am telling may be applicable for one dimensional motion. When I drop an object from a certain height above the ground, object will fall freely under the effect of gravity. While it is falling freely under the effect of gravity, its velocity is increasing or decreasing? Increasing. Velocity is increasing. You know why velocity is increasing? Because the direction of a motion is along the direction of acceleration. As you already know, when the body is dropped from a certain height above the ground, due to acceleration, because of the acceleration due to gravity, it is falling downward. Correct? In what direction acceleration due to gravity is acting? Downward. Acceleration due to gravity is acting downward, and since the direction of motion is also along the direction of acceleration, velocity goes on, increases. Means simple conclusion is, in one dimensional motion, if the direction of a motion is along the direction of acceleration, velocity of the body goes on, increases. Similarly, if I threw a chalk vertically upward, if I threw some object vertically upward, initially when I am throwing it, I am providing some velocity. When the object is moving upward, its velocity is increasing or decreasing? Decreasing. Why it is decreasing? Because once I throw the object, my job is over. After that, body is moving under the effect of gravitational force. No. In what direction acceleration due to gravity is acting? Downward. In what direction chalk is moving? Upward. Since direction of motion is opposite direction of the acceleration, its velocity goes on, decreases. Since direction of motion is opposite direction of the force, its velocity goes on, decreases. I think you understood what I said. Means simple logic is, in one dimensional motion, if the direction of motion of the object is along the direction of the force or along the direction of acceleration, because direction of acceleration is along the direction of the force only, no? F equal to ma, direction of a force and direction of accelerations are same. Direction of force is same as direction of acceleration. In a one dimensional motion, if the direction of motion is along the direction of force or along the direction of acceleration, velocity of the object goes on increases. In one dimensional motion, when if you take an example of throwing object vertical upward, when the object is moving upward, its acceleration is directed downward, velocity goes on decreases, because direction of motion is against direction of acceleration. Remember that conclusion. If a direction of motion is along a direction of acceleration, velocity goes on increases. If the direction of motion is opposite to direction of acceleration, means velocity is decreasing, or other word, during the motion, if the velocity is increasing, means direction of acceleration is along a direction of motion. During the motion, if the velocity is decreasing, means direction of acceleration is opposite to direction of a motion. I hope you followed this. If I use this logic here, concentrate. At the time when I leave the bob from the extreme position, what is its velocity? 0. By the time when the bob is moving from an extreme position to the mean position, its velocity goes on, increases. When the bob is moving from extreme position to a mean position, velocity goes on, increases, indicating that acceleration is along the direction of a motion. It is for sure. When the velocity is increasing, there is an acceleration, no? So, when the bob is moving from a extreme position to a mean position, velocity of the bob is increasing, means surely acceleration is along the direction of motion. What was the direction of motion? Extreme position to mean position. So, direction of acceleration is towards the mean position. See, direction of acceleration is along the direction of a motion. Direction of motion is from mean position to extreme position. Direction of acceleration is along the direction of motion, because velocity is increasing. This is what I said that time. Of course, who is responsible for acceleration, that is the next level of thinking we will discuss. But now for a timing, our main point of discussion is understanding that condition. Okay, fine. Now the bob is at the mean position. When the bob is at the mean position, you know its velocity is maximum. Now by the time it reaches a mean position, since it gains a maximum velocity due to inertia of motion, the bob will start moving towards the other extreme position. When the bob starts moving towards the other extreme position, can you please tell me what about the velocity of the bob? Velocity of the bob goes on, decreases. Why? You have practically noticed it. Since it is moving towards the extreme position, you know its velocity goes on, decreases, and its velocity will become 0 at the extreme position. Velocity of the bob will become 0 at the extreme position. That means here it has a maximum velocity. When it is moving from mean position to the extreme position, when it is moving from mean position to extreme position, its velocity kept on decreasing, means don't you think that the direction of the force, direction of acceleration is opposite to direction of a motion? What was the direction of a motion? From mean position to extreme position. What should be a direction of acceleration? Towards the mean position. Now also what you find is acceleration of the particle is directed towards the mean position. See the first condition, acceleration of a particle is always directed towards a mean position. Particle may be moving from a extreme position to a mean position, or from mean position to extreme position. Every time acceleration is directed towards a mean position only. Correct? Let us continue. Again, when the bob reaches extreme position, its velocity has become 0, right? Its velocity has become 0. Again the bob will start moving back from extreme position to a mean position. Why it is moving, you may be knowing the answer, we will discuss about that later, but I am comparing the practical fact, what is happening. Based on that I am trying to understand a condition. Reason behind that in terms of physics we will discuss later, why it is coming back towards the mean position, why velocity is decreasing when it is moving towards extreme position, everything we will discuss. When it is coming back towards a mean position, again you know that from an extreme position to a mean position, when it is moving, its velocity goes on, increases. Velocity is increasing means obviously the direction of acceleration is along the direction of a motion, that is why velocity is increasing, or direction of the force is along the direction of motion, that is why velocity is increasing. Now when the bob is moving from extreme position to mean position, velocity is increasing, indicating that direction of acceleration is along a direction of motion. What was the direction of motion? Extreme to mean position. Even direction of acceleration is also towards the mean position. It is directed towards the mean position. By the time it reaches the mean position, its velocity is maximum. Due to inertia motion, again it will start moving towards other extreme end. While it is moving towards other extreme end from mean position to the extreme end, what about its velocity? Goes on, decreases. Upward arrow indicates increases, downward arrow indicates decreases in my explanation. Velocity goes on, decreases. When the bob is moving from mean position to extreme position, velocity is decreasing, means force is acting opposite direction of motion, means acceleration is acting in a direction opposite direction of motion, correct? So I can say that acceleration is directed towards again the mean position. What do you notice in my explanation, throughout my explanation, that bob may be moving from extreme position to mean position, or from mean position to extreme position, again from extreme position to mean position, again from mean position to extreme position. Every time you find that acceleration of the bob is always directed towards the mean position. Every time you find that acceleration of the bob is always directed towards the mean position. That is the first condition. A particle is said to have a simple harmonic motion if the acceleration of the particle is always directed towards the mean position. Every instant of its motion, what you find is acceleration of the bob is always directed towards the mean position. Who is providing that acceleration? You might be knowing, but we will discuss it separately later. I think you understood this. See the next one. Magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. Magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. What do you mean by that? So before I convince you the second condition, I think all of you understood the first condition. Acceleration of a particle is always directed towards the mean position, because acceleration is a vector indicating that it is always directed towards the mean position during the simple harmonic motion. Before I convince the second condition, I would like to tell you one more thing here. When you speak about displacement of the particle from the mean position, means displacement is always measured from the mean position. Displacement is always measured from the mean position. Displacement may be this much or this much or this much. It is always measured from the mean position. It is just like mean position is acting like a origin in the measurement of a displacement. Even when you speak about displacement in upward direction here, displacement is measured from the mean position only. Even here also in the example of oscillation of pendulum, the displacement is measured from which position? Mean position. See. When the bob is at the extreme position, can I say displacement is maximum? Yeah, displacement has to be measured from mean position. When the bob is left from the extreme position, it will start moving towards a mean position. Displacement is again measured from the mean position. I think you are able to follow. To get a more clarity, look at this. This is the mean position of the pendulum. You have taken a bob to an extreme position. When you leave the bob from the extreme position, it will occupy different positions. It is only one pendulum, different positions. This is one displacement y1. This is another displacement y2. This is a one more displacement y3. I hope you are able to follow. This is a one more displacement y4. y1, y2, y3, y4. y1, y2, y3, y4. Displacement is measured from the mean position. Even this side also. Are you able to follow? Displacement can be to the right side, displacement can be to the left side. If it is a one dimensional one, you can take one particular direction of displacement as positive, other particular direction of displacement as a negative. Keep it in mind. Okay, let us try to follow the second condition. First, we will taking an example of a pendulum. Then after that, I will take an example of a spring also in convincing it. Actually, I can convince that second condition with the help of a spring very easily. Let us try that first. See here. First condition easily followed by taking an example of a pendulum. I will convince the second condition even in the pendulum later. Be involved, try to understand what I explain. There is a spring which is fixed to a rigid support, and to the free end of the spring you have added some load, correct. In order to give an oscillation, you will stretch a spring through a distance x. You will stretch a spring downward through a distance x. Can I say that x is an amount of a displacement, amount of a elongation of a spring, amount of a stretching of a spring in the presence of an external applied force. I applied some force in order to stretch a spring. You have learnt already in a topic called Newton's laws of motion, work energy power. When a spring has been stretched through a distance x by the application of external force, due to a property called elasticity, one more force is developed in the spring. That force developed is equal in magnitude to the applied force, but starts acting in a direction opposite to the applied force, and you call that force as a restoring force. In the case of a spring, that restoring force was called as a spring force. And the spring force developed was equal in magnitude to the applied force, but starts acting in a direction opposite to the applied force. In what direction you have applied the force? In pulling a spring downward, in downward direction. And at the same time, due to a property called elasticity, one more force is developed in the spring which is equal in magnitude to the applied force, but acting in a direction opposite to the applied force. We call that force as a restoring force, and it has been given an explanation also why that force is called as a restoring force. Of course, you might have represented a restoring force by the symbol Fs, but you know that it is equal in magnitude to the applied force, correct. So, restoring force is given by the formula minus Kx in the case of a spring. Restoring force, now I am going to represent as F only, and here the indicating it is a restoring force, the negative sign indicating that force developed is opposite to direction of a displacement. Force developed is in a direction opposite direction of a displacement. You are pulling a spring downward by applying a force. At the same time, due to a property called elasticity, one more force is developed. That force is equal in magnitude to the applied force, but acting in a direction opposite to the applied force and opposite to direction of a displacement. Applied force and displacement are in same direction, but restoring force is opposite to direction of a displacement. That is why that negative sign is there. We know that this F is directly proportional to x. Applied force is directly proportional to a displacement, but restoring force is directly proportional to minus of displacement, correct? Yes. Then we replace the proportionality by a constant k. It is called force constant. In the case of a spring, it is called spring constant. The point to be highlighted is I have used a word called restoring force. Restoring force. Why it is called restoring force? You know the reason now. If I release this mass, I have pulled this spring slightly downward by applying some force. If I remove that force by releasing that mass, because of this force developed due to property of elasticity, don't you think that spring will be tried to be restored back in its original position? Yes, that's why it is called as a restoring force. Same restoring force you can expect there also. Who is acting like a restoring force? We will discuss in the case of pendulum later. Now let me wind up this. This restoring force is given by the formula minus Kx, correct? And because of restoring force only, the spring will try to come back to its mean position. By the time it reaches mean position, it will gain some velocity. Because of velocity, due to inertia of motion, it will go slightly above its mean position. Again, while it is moving above its mean position, restoring force is developed in a direction opposite direction of displacement. When it is moving above its mean position, displacement is upward, restoring force will be developed downward, correct? Again, after reaching the extreme position, its velocity will become 0. Again, due to restoring force, again try to come back to its mean position. Means the spring will exhibit a simple harmonic motion. I hope you are able to follow. See, the one word I introduced called restoring force, which is actually responsible for bringing the spring back to its mean position. And in our earlier discussion, we stopped our discussion just by bringing the spring back to its mean position. But here what happens is, by the time it reaches mean position, due to inertia motion, it will go slightly above its mean position. While it is moving above its mean position, again the restoring force is developed in a direction downward, opposite direction of displacement. And because of restoring force only, at one particular position its velocity will become 0. Again try to come back to its mean position, spring will execute a simple harmonic motion. That means, once you stretch a spring through a distance x, after that if you leave it, who is responsible for bringing the spring back to its mean position? Restoring force. and that restoring force is obviously directly proportional to displacement. That is the point to be noted. And that restoring force is given by the formula minus kx in the case of a spring, and if I say that this force can be replaced as m into a, general formula for any force, it is a mass into acceleration, and the same force here, it is nothing but minus k into x, right. In this case, if I equate the two, m into a is equal to minus k into x, m into a is equal to minus k into x, a is equal to minus k into x by m. Look at this. Of course, instead of x you could have taken it as y also, that is your choice. If you think that this is a vertical motion, I would like to take it as y, not a problem. I could have taken it as f is equal to minus ky also. Instead of x, I could have taken it as y. It is your choice. Don't have any confusion with the terms used. I took a displacement as x instead of x, since if you compare this with the y axis, you could have taken it as y. Nothing wrong in that. Now coming back to this, don't you think that for a given spring k is a constant, spring constant, m is a mass which you attached is a constant, what you find is a is directly proportional to x. Of course, negative sign indicates what? Acceleration and displacement are in opposite direction. Okay, I will put negative sign out of this. A is directly proportional to x. Minus x, minus indicates in that acceleration and displacement are in opposite direction. That is the meaning of a negative sign here. I said no, instead of x you could have taken it as y. Instead of x you could have taken it as y. Ma is equal to minus k into y. Here also a is equal to minus k by m into y. Here k by m is a constant, a is directly proportional to y. That is the meaning of the second condition which you can make out there. Magnitude of the acceleration is directly proportional to the, see this, magnitude, forget about negative sign just indicating that acceleration and displacement always in opposite direction, you can make out. Magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. This is a proof, mathematical proof. Means during simple harmonic motion that a is not constant, not uniform. That is a very important one. During simple harmonic motion, this a is not uniform, a is directly proportional to x. Magnitude of a is directly proportional to the displacement of the particle from the mean position. That is the meaning of second condition, that is proved in the case of a spring using equation. Now let us try to understand in the case of pendulum also, that is different. Now let us try to follow first of all, a and displacement are in opposite direction. What is the direction of a always according to first condition? Acceleration is always directed towards the mean position. Particle may be moving from extreme to mean position, mean to extreme position, a is always directed towards the mean position, it is already proved, correct? Now here we want to understand how a and y are in opposite direction. What is the direction of a displacement always? From the mean position, from mean position to the new position, mean position to the new position. But every time acceleration is always directed towards the mean position only, no. Acceleration is always directed towards the mean position, displacement is always directed away from the mean position, from the mean position to the position of the particle. Displacement, look at this diagram also. Acceleration is always directed towards the mean position, but displacement is always directed away from the mean position. Acceleration is always directed towards the mean position during SHM, whereas displacement is always directed away from the mean position. From the mean position you have to measure a displacement, that is the meaning of a negative sign. I believe you followed. Okay. Coming to that point, like how to understand this particular point in the case of a pendulum. Magnitude of the acceleration is always directly proportional to the displacement of the particle from the mean position. For that, you should know why the bob left from the extreme position will start moving towards the mean position. I said for that you should know why the bob left from the extreme position will start moving towards the mean position. If I ask with you, why the bob left from the extreme position will start moving towards the mean position. Means when you remove this force, you have held the bob at the extreme position. When you remove that force F, why the bob will start moving towards the extreme position? Surely you will come out with the answer that because of a gravitational force. But my question to you is, when you leave the bob from that extreme position, please be involved in understanding what I am telling you now. This was a mean position. When you leave the bob from this extreme position, where in the extreme position the thread is making an angle theta with the vertical or original position, you have removed F. You have removed F, but there is mg. You said, most of you are having an answer in your mind that when the bob is left from extreme position, it is starting moving towards the mean position because of gravitational force. But gravitational force is acting vertically downward. No, mg. Mg is acting vertically downward. But why it is moving towards the mean position? Your answer will be, since it is tied using a string, that is why it is unable to move vertically downward, it is moving towards the mean position. Practically whatever you said is right, nothing wrong in that. Since it is tied, if it was a free, it would have fallen vertically downward, correct? Since it is tied using a string, it will start moving towards the mean position. But reality is, when you leave the bob from the extreme position by the removal of this F, surely there is a tension in the string, there is mg. There is a one component of mg is acting in a direction towards the mean position. There is a one component of mg acting in a direction towards the mean position. Mg is a force. Component of mg is also force, no? Now that is a restoring force here. In the case of a spring, you know, there is a restoring force developed. Here, when you leave the bob from extreme position, one component of mg which is acting in a direction towards the mean position will be a restoring force. That is responsible for getting the bob back from extreme position to a mean position. Which is that component? That component can be found here. When you remove that F, horizontal force with which you held the bob, now see, I can continue my explanation. See, this is a vertical direction, this is theta, means even this is also theta, and I can extend this direction of a thread in the opposite direction. When this is theta, even this is also theta, correct? Simple mathematics, I think you understood. This is a straight line, this is also extended line. When this is theta, this is also theta, correct? Simple mathematics. When this is theta, even this is also theta. Now, can I say these two are perpendicular to each other? This dotted line and this whatever the line with an arrow mark I drawn is perpendicular to each other. What is the component of mg in this direction? It is mg cos theta. Resolution. Mg has been resolved now. One component of mg is mg cos theta is acting in a direction opposite to tension. One more component of mg is there, no, that is mg sin theta, exactly. That is a restoring force. Mg sin theta is a restoring force. Because of that mg sin theta will only that bob is tried to be stored back in its original position. Just like there you had restoring force kx minus kx. Here also restoring force is, I can say, minus mg sin theta, because minus mg sin theta is acting in a direction towards the mean position. And moreover, if you want a more clarity, that mg sin theta is a tangential to this arc. You know that when the pendulum is left from the extreme position, it will start moving towards the mean position in the part of a circle. That mg sin theta is a tangent to that, mg sin theta. Mg sin theta is acting in what direction? Towards the mean position. Displacement is acting in which direction? Towards the extreme position. So since this restoring force is acting in a direction, opposite direction of a displacement, I can write restoring force as minus mg sin theta. If this is minus mg sin theta, restoring force is mg sin theta, of course I can write minus mg sin theta because it is acting in a direction, opposite direction of displacement. Don't you think that this is comparable with F is equal to m into A again? So this comparison you can do. Now tell me, if I compare it just like earlier also F is equal to ma is comparable with F is equal to minus kx. Here F is equal to ma is comparable with F is equal to minus mg sin theta. Can't you get the answer for A? Yeah, just compare it. M is common. What is A then? Minus g sin theta, exactly. A is minus g sin theta. Or if you don't include a negative sign also it will become g sin theta. A is, what do you think? A is a constant or a variable? Obviously variable. G is a constant. A is equal to g sin theta, no. A is equal to g sin theta. Why minus g sin theta? Because the direction of the acceleration is opposite direction of displacement, only that reason, no other reason. Okay, g is constant, but theta is variable. When the bob was left from extreme position, when the bob is at the extreme position, theta is highest, sin theta is maximum, g sin theta is maximum. When the bob is left from extreme position, the bob will start moving towards the mean position, theta goes on decreases, sin theta also goes on decreases, g sin theta also goes on decreases. Means again coming to that point, A is not a constant one, its magnitude is also not constant, its value keeps on changing. Where it is maximum according to this? Can I say that when the bob is at the extreme position, displacement is maximum? When the bob is at the extreme position, displacement is maximum. When the bob is at extreme position, don't you think that this acceleration g sin theta is maximum? Theta is maximum, sin theta is maximum, g sin theta is maximum. When the bob is left from the extreme position, bob will start moving towards the mean position. When the bob starts moving towards the mean position, don't you think its displacement goes on decreases? Displacement is measured from the mean position. Displacement is measured from the mean position. When the bob keeps on moving towards the mean position, its displacement goes on decreases. See, y1, y2, y3, y4 goes on decreases, no? When the displacement decreasing, even acceleration g sin theta is also decreasing. That is the meaning of the second condition. Acceleration is directly proportional to the displacement of the particle from the mean position. And negative sign in the equation just indicating that acceleration and displacement are in opposite direction. Acceleration is always directed towards the mean position, displacement is measured away from the mean position. From the mean position you have to measure a displacement. That is the meaning of a negative sign. I think you got a clarity regarding the conditions for a simple harmonic motion. Please remember everything whatever I explained in detail. Of course, the explanation given related to the g sin theta there, actually that mg sin theta is a restoring force there. Here it is taken as minus mg sin theta because it is the direction of acceleration is the direction of that force is opposite to displacement. Direction of force is opposite to displacement, direction of acceleration is also opposite to displacement. And there mg sin theta is a restoring force. Acceleration is g sin theta, it is not constant. When the bob is moving towards the mean position, g sin theta goes on decreases. When the bob is at the mean position, what is the value of g sin theta? 0. What is the displacement? 0. Second condition is very much clear now. Magnitude of the acceleration is directly proportional to the displacement of the particle from the mean position. When the displacement is maximum, acceleration is also maximum. When displacement is 0, acceleration also becomes 0. I hope you are able to follow. So please remember these two conditions which was explained to you, very much needed. I believe everything related to the condition is clear to you. Remaining things will continue in the next session. Thank you very much.